Hello everyone, welcome back to our college algebra course. Today I'm going to cover three sections, 2.2, 2.3 and 2.5. Those are the last three sections of chapter 2. We skipped 2.4, it's about circle. Alright, so let's start with section 2.2. We'll be talking about graph of equations and intercept and symmetries. So basically three things: graphs, intercept, and symmetry. 2M for symmetry. Okay. This is how we're gonna cover this section today. Okay, I'm gonna give you the idea, the concept first, and I'm gonna give you a bunch of examples, and hopefully you guys gonna see the idea and learn from the example. So let's start with the first one, intercept. Intercept. Okay. So let me just sketch a very random graph. Say you have a graph. Okay. We have two types of intercept, and the name says it all. Intercept is a point where the graph intersects either the x-axis or the y-axis. Okay. So this point right here is called the y-intercept because that's the point where the graph intersects the y-axis, and we only have one y-intercept. This point, and that point is called the x-intercept because the graph intersects the x-axis. Okay, and as you see right here, all the points on the y-axis got the y component equal to 0. I'm sorry, the x component is 0, so this point is like 0, comma some y, right? Y. So this one is like x1, x2, x3. So this point right here is like x1, comma 0, x2, comma 0. And then this point right here is x3, comma 0, where x1 and x2, x3 are some x coordinates. Okay? So let's give us a hint of how to find a intercept. For the y-intercept, you let x equal 0 and solve for y. For the x-intercept, you see all the y components are 0. So you let y equal 0 and solve for x. So for x-intercept, let y equal to 0, then solve for x. Keep in mind, I'm just giving you the idea for now. Okay? And then later on, I'll give you a bunch of examples and you'll see more in numbers. For y-intercept right here, you let x equal to 0. Then solve for y. That is the first part about the x-intercept and the y-intercept. Second, we're going to talk about symmetry. What's the 2F for symmetry? But we're going to have, I think, three types of symmetry. Let me show you the first one. Look at the graph right here. This one right here, the graph is symmetrical about the y-axis. Okay? Symmetrical about the y-axis, see? Look at the graph. Actually, this one is a parabola. The left-hand side parabola and the right-hand side of the parabola, if you reflect about the y-axis, is on top of each other. Okay? And the probability for having symmetry about the y-axis is take a look at any point on the graph. Say this point right here. Assuming this is like 1, and this is 3. And if you flip over the y-axis, you're going to have another point. This is what? -1, and this is 3, right? So in general, if you have a point x, y on the graph, in general, okay? And if the graph is symmetrical about the y-axis, you flip it over. The y coordinates stay the same. The x is going to change, so the second point is going to be x comma -y. Okay? So you flip over the y-axis. And similarly, the second type of symmetry is about the x-axis. Say if I have a graph like this. Now I'm drawing another parabola. Keep in mind, this is not a function, all right? We don't talk about function. We just say graph in general. And you see what? If you have any point in general in here, say x comma y, and if the graph is symmetrical about the x-axis, it means what? You flip a point, a random point on the graph over the x-axis, the second point is still on the graph. You see what happened in here? You flip over the x-axis, the x components stay the same, x coordinates stay the same, but y right here, gonna flip, change to negative y. So if the second point is xy, then you flip over the x-axis, the other point gonna be x comma negative y. I was wrong in here. This one is gonna be, excuse me, fix that for me. This is gonna be negative x comma y, should be, right? You flip over. This is x or negative x. Fix that first part for me. This is symmetrical about the y-axis. Okay. What do? We change x to negative x. And for second one right here, we are changing y to negative y. Okay? So for symmetry about the x-axis, you change y to negative y. Okay? And there is one more type of symmetry that you guys are going to see. This is more special than the previous ones. Take a look at this graph, guys. This is my x-axis, and this is my y-axis. This, we talk about symmetry about the origin. So what are we talking about here? So you have a point on the graph, x comma y, this is x, and this is y, and we say that this graph is symmetrical about the origin. And what do we mean is, if we flip a point about the origin, flip it over the origin. So if a point right here, you reflect over the origin. We still have another point right on the graph. And if that happens, we say that the graph is symmetrical about the origin. So if the point is xy, you flip about the origin, but you change both x and y. So the second point right here, this is going to be negative x. This point right here is going to be negative y. So we're going to change x to negative x and y to negative y. All right. So whenever you guys see a graph that satisfies this property, you change x to negative x, you change y to negative y. Is that point still on the graph, or we have the same equation? Then the graph is symmetrical about the origin. Okay? So actually there are some graphs that have no symmetry at all, and some graphs got all the symmetries. Let me show you examples. All right, first example. So number 3. Examples. Very first one. Give you a line then. Simple one. Y is equal to 2x minus 1. Alright? Later on, we're going to learn that this is equation for line slope is 2, y-intercept is negative 1. I bet many of you guys know it already. And the very manual technique to graph any equation in general is something called plotting points. Excuse me. Plotting points. What do we mean by that? We're gonna construct a table, right, with 2 columns, x and y. We plug in some value for x. We calculate y. We have some points. Okay, the more points we have, and the more accurate your guess of the graph is gonna be. If I plug in x equals 0, easy point, right? 0 for x, 2 times 0 is 0, minus 1. I got negative 1 for y. And what does it mean by this? The point x0, y negative 1 will be on the graph. Okay? Try another point. Say x is 1, and 2 times 1 is 2 minus 1. I got y is 1. The point 1, 1 will be on the graph. And since I know this is a line already, technically I'll only need 2 points to graph a line. But let's get some more. Say x equal to 2. 2 times 2 is 4, minus 1, I got 3. Try some negative number. X is negative 1. 2 times negative 1 is negative 2, minus 1 is negative 3. So negative 1 here. And negative 3 here. So we have a couple more points. X is 2. 1, 2, 3. Right here. X is negative 1. Y is negative 3. Somewhere in here. Let me use different color. Okay. So I can have a line. Okay? Now, we can talk about the x-intercept and the y-intercept of the line. This one has any, well, I see it right here. It's got a y-intercept right here, right? You plug in x equals 0. That's what we did right here. The y-intercept is at negative 1. So this is 0, comma, negative 1 is the y-intercept. What about the x-intercept? Recall what we just talked about a couple of minutes ago. What we're going to do to find the x-intercept? I see one right here. How do we find that point? We're going to plug in y equal to 0 and solve for x, right? So for the y-intercept, I'm sorry, for the x-intercept, you plug in y equal to 0. So for x-intercept, let y equal to 0. Let y equal to 0. So I got 0 is equal to 2x minus 1. Of course, I can solve for x from here. Add the 1 on both sides, got 1 equal to 2x. Divide by 2, I got x equal to 1/2, which is 0.5. So the point right here is the x-intercept at where? 1/2 for x and 0 for y. You got the intercepts. What about symmetry? By looking at the graph, I can tell you right away that this graph has no symmetry at all. There is no y symmetry, no x symmetry, and no origin symmetry. No symmetry about the x-axis, no symmetry about the y-axis, and no symmetry about the origin. See why? When I flip the graph, I flip a point, any point, right? I choose a point. I only need one point to prove it, but you see any point here, except for that point. You have a point on the graph, you flip over the y-axis. This point right here is not on the graph, so it's not symmetrical about the y-axis. Similarly, I have a point, I flip over the x-axis. I have a point that's off the graph, not on the graph, so it's not symmetrical about the x-axis. And same thing here, I have a point, choose any point, okay? I flip over the origin, watch me, this is my origin, right? This is a point I choose, I flip over the origin. I got a point right here. And the second point is not on the graph, so it's not symmetrical about the origin. So this graph right here has no symmetry. No symmetry. Okay? The question is, can we do it algebraically? In other words, can we do it more professionally instead of saying by looking at the graph, we see there's no symmetry? And the answer is yes, based on the algebra that we have. So you want to test for symmetry, you're going to plug in the variable for x and y. We change the variable for x and y. So first of all, I'll show you how to test for symmetry about the y-axis. To test for symmetry about the y-axis, you want to test for symmetry about the y-axis, you change the point, right? Change the x-coordinate of the point, right? You flip over the y-axis. What do you need to change? You change the x to negative x. You keep the y the same. You change x to negative x. And keep in mind that we cannot plug in any specific point to test in general, because if you want to disprove something, all you have to do is give an counterexample. But if you really want to prove something that is correct, you have to prove it's true all the time. So you cannot plug in like, oh, I plug in the point x equal to 1, x equal to 2, and it works, therefore it works all the time. But if you want to disprove something, you plug in a point and it doesn't work, you can say that, oh, it's not going to work. Okay? You want to prove something that works all the time, you have to prove that it works forever, all the time, for any x. So what do we do? I have the original equation, y equal to 2x minus 1. Is that right? Now I'm changing x to negative x. I got y is equal to 2 times negative x minus 1. What am I doing right here? Whenever I see a letter x from my original equation, I change to negative x. So this is my original equation. This is my new equation. Okay? And of course, I can go ahead and simplify the new equation. I got y equal to negative 2x minus 1. You see what? Those two equations are not the same. Right? So it's no symmetry. No symmetry about the y-axis. Okay? Not the same. Okay? Similarly, if I want to test for symmetry about the x-axis, then I'm going to do this. Let me cheat a little by not erasing everything. We'll test for symmetry about the x-axis. Instead of changing x to negative x, test for symmetry about the x-axis right here, right? In other words, we have to flip a point from above the x-axis to the point below the x-axis. So what am I changing? Am I changing the y value? Yes. So change y to negative y. So my original equation is y equal to 2x minus 1. Whenever I see a letter y, I'll change to negative y. I will have negative y equal to 2x minus 1. When you guys see that the two equations, they're not the same. When you want to simplify this a little, divide the second equation both sides by negative 1. I got y equal to negative 2x plus 1. Okay? So my new equation and my original equation are not the same again. And that means the graph is not symmetrical about the x-axis, because when you change y to negative y, you're going to come up with a new equation or a new graph. It's not the same graph anymore. And similarly, if you want to test for symmetry about the origin, you change both y to negative y and x to negative x. Okay? So my original equation is y equal to 2x minus 1. My new equation, whenever I see a y, I will change to negative y. Whenever I see a letter x, I'll change to negative x. And then I keep everything else the same. And let's simplify this. Negative y equal to negative 2x minus 1. Divide both sides by negative 1. I got y equal to 2x plus 1. Because divide both sides by negative 1, divide by negative 1, divide by negative 1. And I'm comparing the original equation to the new one. This is 2x minus 1. The new one is 2x plus 1. It's not the same again. So it's not symmetrical about the origin. Okay? Not symmetrical about the x-axis, not symmetrical about the y-axis, not symmetrical about the origin. So this graph right here, this line right here, got no symmetry at all. This is what we planned from the beginning by looking at the graph. But eventually, later on, you guys see many exercises, many problems. They give you the equation without showing you the graph, and they ask you to prove to find any symmetry. You cannot just you cannot just plug in the graph and say by looking at the graph we say that is not a proper way to prove something. But well, the graph is going to give you a hint, right? But you want to prove something properly, you really have to use algebra, and that's why we have college algebra course. Next, let me give you another example, and this time, hopefully, it's going to have some kind of symmetry. How about this? That's y equal to x squared minus 1. This time I'm giving you a problem. Okay? And I can sketch a graph, see how it looks. X, y. Plug in x equal to 0. I can have y equal to 0 squared minus 1 is negative 1. Plug in x equal to 1. 1 squared is 1 minus 1 is 0. X equal to 2. 2 squared is 4. 4 minus 1 is 3. X equal to negative 1. Negative 1 squared now becomes 1. 1 minus 1 is 0. X equal to negative 2. Negative 2 squared is 4. 4 minus 1 is 3. And of course you can plug more points, but let me just do 5 points right there. And I can sketch a graph, see how it looks. X-axis right here, y-axis right here. X is 0, negative 1. X is 1, 0, 2, 3. X is 2, 1, 2, 3. This is -1, 0, and -2, 3. And let me use green color this time. And I claim that when I sketch a graph, I got something like this. Oh. Okay. So you guys see that this graph actually is, we know the name of it, it's called a parabola. It actually has some x-intercept and y-intercept. So we can take care of that part first before we're talking about symmetry. This point right here is the y-intercept. Those 2 points right there are the x-intercept, right? So for the y-intercept, what do? You plug in x equals 0. You find the y-intercept. Y-intercept. Let x equal to 0. So you got what? Y equal to x squared minus 1. Plug in x equals 0. Y equal to 0 squared minus 1 equal -1. We actually did it already right there. So the y-intercept is at 0, -1. Okay? Now, what about the x-intercept? We actually have 2 of those. Okay? So how do we solve for this? We plug in y equals 0, right? For x-intercept, you let y equal to 0. You got what? Y equal to x squared minus 1, 0 equal to x squared minus 1. Now there's 2 ways to actually solve this problem. And the way that I usually do, I see is quadratic. So I've tried to factor this out. I use quadratic formula. 0 is equal to x minus 1 times x plus 1. And then you guys going to have 2 solutions in here. X minus 1 equal to 0 or x plus 1 equal to 0. Then you got x equal to 1 or x equal to -1. This point right here is 1, 0. This point right here is -1, 0. 2 x-intercept. Another way which is easier for now for this specific equation is you add 1 on both sides. You have 1 equal to x squared. And now here comes a little problem to some people. They say x squared equal to 1. And then you say, oh, x equal to 1. Take square root of both sides. So x equal to 1. We'll draw it right here, x equal to 1. But actually it's not enough, because actually there are 2 values that make 2 values of x and make x squared equal to 1. This is x equal to square root of 1, right? Both sides, but you need to have a plus or minus, which is x equal to 1 or x equal to -1. Because 1 squared equal to 1, but another value squared equal to 1 is -1. -1 squared is also equal to 1. So even though the first way that I'm showing you right here may be longer, but it's guaranteed that you cover all the solution. This one is shorter, but be very careful, okay? It's up to you. So when this graph right here show you that it has 1 y-intercept, 2 x-intercept, and it has some kind of symmetry. You guys see it? This is symmetrical about the y-axis. See the left and the right points reflect each other from the y-axis. Of course, it doesn't have any symmetry about the x-axis. You have a point right here. You flip over the x-axis. You don't have a point on the graph. You have a point here. You flip over the y-axis. You have a point still on the graph. Any point. Any point. All the points on the graph. Flip over the y-axis. You still have a point on the graph. So it is symmetrical about the y-axis, but not the x-axis, not the origin. See, I have a point, say, right here. If I flip over the origin, this is my origin, okay? I have a point right here. I flip over the origin, I have a point right there, not on the graph. So this point right here, I flip over the origin, I got a point right there, not on the graph. So it's not symmetrical about the origin. Only, we only have symmetry about the y-axis. We're going to test them off. See if the algebra convinces our observations about symmetry. Y equal to x squared minus 1. Is that right? I want to test for symmetry about the y-axis. About the y-axis, what do we need to do? Flip over the y-axis. We are changing x to -x. So this is my original equation. I don't think I have to write it again. For new equation, I change x to -x, right? I got what? Y equal to -x. See, x changed to x and then square it up, minus 1. You see what happened in here? I keep everything the same, except for x. Whenever I see the x, I'll change to negative x. And I can simplify this equation. This is what? Y equal to x squared minus 1. Make a double negative, make it positive as well. And you see what? The original equation and the new equation is actually the same. And what does it tell you? It is symmetrical about the, yes, it is symmetrical about the y-axis. Because the algebra say that, okay? The algebra shows us that whenever you change x to negative x, you see, in other words, you are flipping the point about the y-axis. You change x to negative x. I still have the same equation. I still have the same graph. So if you flip the point over the y-axis, you still have a point on the graph. It is symmetrical about the y-axis. Now, we test for symmetry about the x-axis. My original equation is y equal to x squared minus 1, right? To test about the x-axis, okay? What do we need to change? Flip about the x-axis, we change y to negative y. Y to negative y. We have negative y equal to x squared minus 1. Okay, I keep everything else the same. Y, except for y now becomes negative y. And that simplified the equation. We got y is equal to negative x squared plus 1. You see how I got from here to here? I divided, or I multiplied both sides by negative 1. I have it. And I compare the new one to the original one. Not the same. Not the same. This is x squared minus 1. This is negative x squared plus 1. Not the same. Okay? And what does it say? The graph is not symmetrical about the x-axis. Okay? Now test about the origin. What do we do to test for symmetry about the origin? We flip both x and y. Okay? The point right here. Flip over the origin, we change x to negative x and y to negative y. Okay? So my original equation is y equal to x squared minus 1. Whenever I see a y, I change to negative y. Whenever I see an x, I'll change to negative x. And then x squared now becomes negative x squared and then minus 1. And simplify, I got y, negative y equal to x squared minus 1. Because this negative x, everything squared is just x squared. Now, divide both sides by negative 1, or multiply both sides by negative 1. I got y equal to negative x squared plus 1. Right? Multiply both sides by negative 1. I got this. Okay? And of course, it's not the same with the original equation. So not the same. This is my original equation. This is my new equation. Not the same. Not the same. So what do we say? No symmetry about the origin, no symmetry about the x-axis, and yes, we do have symmetry about the y-axis. Okay? Show you another example. How about this? Y equal to x cubed minus 4x. Okay. By the way, this x cubed later on we're going to call it the cubic function, or call it a polynomial of degree 3. Okay. And of course we can sketch a graph, make a table. Okay. X, y, and plug in some value for x. X equals 0. We got y equals 0. Try x equal to 1. This is 1 right here, minus 4 is negative 3. X equal to 2. 2 cubed is 8. 8 minus 8 is 0. X equal to 3. 3 cubed is 27. Oh boy, it's going to get bigger, right? 3 times 4 is 12. 27 minus 12 is 15, I think. Check my algebra.